In this video, we're going to discuss the graphical analysis of motion, and we're going to distinguish the two different types of motion. But in order to do that, we're first going to look at a few example graphs that typically emerge in the typical introductory physics textbook. Then what we're going to do is we're going to distinguish the difference between constant velocity and constant acceleration by looking at the displacement velocity and acceleration versus time graphs given different initial conditions. And then we're going to dissect all the gruesome details of a few examples of the two different types of motion. So we can break motion down into two distinct types. Now in an introductory physics course, we often talk about objects that move with constant velocity, and we contrast that with objects that move with constant acceleration. So what's the difference between the two different types of motion? So for an object that's moving with constant acceleration, we like to say that the object is speeding up or slowing down. Its velocity is changing, it is not constant. So in the case where an object's velocity is increasing, we often say that it's speeding up, and for an object that's slowing down, the velocity is decreasing. This is different from an object that moves with constant velocity, in which the speed and direction the object is traveling do not change. So the velocity remains the same. Now, one of the things that you should know is when an object's not speeding up or slowing down, that is, when it has constant velocity, the acceleration of that object is also zero. For an object moving with constant acceleration, the acceleration is going to be either greater than zero or less than zero, but it's not going to equal zero. Now, if we look at a set of graphs for an object moving with constant velocity and compare them to a set of graphs for an object traveling with constant acceleration, we can generate a couple examples. This is your typical constant velocity set of graphs that you see in an introductory physics textbook. For an object moving with constant acceleration in which the velocity is increasing or decreasing, you often see a set of graphs like this in a typical textbook. But these sets of graphs, the displacement velocity and the acceleration versus time graph, are one of an infinite number of examples. An equally valid set of graphs would look like this, in which case the displacement versus time graph looks a little bit different than the previous graph, but the only difference is the initial position that the object started at. And we're going to talk about what the initial position actually means as we go further into this video. But one of the really interesting things is even though that the initial position changed in both sets of these displacement versus time graphs, the velocity versus time graphs and the acceleration versus time graphs remain the same. Go back and check that out as we go forward. Now, another set of graphs that we can make, which are also equally valid to present in a textbook but never are, is by having the object start some distance away from the observer, in which case we can represent that with a delta x, which I actually should have just written it as x initial, the initial position, but in this case I wrote it as delta x, which I apologize for. But notice that the velocity versus time graph and acceleration versus time graph remain the same. Another set of graphs that we could take a look at would look like this, in which case the velocity versus time graph for both of these has changed, and the displacement versus time graph for both of these has changed, as well as in the case of an object moving with constant acceleration, this graph has changed as well. We're going to talk about why these changes occur given different initial conditions. So let's talk about what initial conditions are. We can talk about where the object is initially. So the initial position is where is the object initially with respect to the observer, the person making the measurements of its initial position. Then we can talk about an object's initial velocity, and that tells us how fast or slow and in what direction the object is initially traveling. Then we can talk about acceleration, which would answer the question is the object speeding up or slowing down, which ultimately tells us if the object is moving with constant velocity or constant acceleration. So now let's talk a little bit about graphs, and in this case we're going to talk about constant velocity graphs, then we're going to go into constant acceleration graphs. Now, an object that moves with constant velocity is going to move equal distances in equal amounts of time. But not only is it equal distances in equal time, the object moves in the same direction. So we often describe it with this other word called displacement. So the displacement of this object every single second in this case is going to be the same. And I can represent that with a displacement vector. And what you should notice is that the displacement vector of each one of these is the same length, because it's not only moving the same distance, but is also moving the same direction. We can draw the velocity vector in the same direction. The velocity vector is always going to be in the same direction as the displacement vector. And so one of the things that we can say is, if an object has positive displacement, it's going to have positive velocity. Now, one of the things that we should have brought up is, in this case, we're going to have the observer, the person watching where this car goes every single second, right here at the origin. In this case, we're going to have the observer standing right here, still at the origin, but in this case, the car is going to approach the observer. And so what we're going to see is, we're going to record negative displacement. In this case, the displacement vector, in each case, are equal in magnitude and in the same direction. Constant velocity. So I can also draw a velocity vector in the direction that this car is moving. Again, notice that the displacement vector is pointing in the same direction as the velocity vector. And one of the things that we're going to talk about is negative displacement implies that the object has negative velocity. Since we're talking about displacement and distance, let's distinguish the two words. Now, when you and I use the word distance, we often refer to how far something travels. We don't care about in what direction when we use the word distance. And that's to contrast it with displacement, which not only tells us how far away an object is or is traveling, but it also tells us in what direction the object is traveling as well. And two other words that we often use are velocity and speed. Now, speed just tells us how fast something is traveling. It doesn't tell us what direction it is traveling. And that's why in physics we use the word velocity, because velocity tells us how fast or slow an object is traveling, but also in what direction. So it tells us a lot more information about how the object is moving. Now, one of the things about velocity is it can be positive, negative, which would indicate an object moving in, say, the positive x or the positive y direction, or negative, in which case an object is moving in the negative x or negative y direction. So velocity can tell us if an object is moving forward, backward, up, down, left, right, or any of the other words that we use to describe direction. Now, a typical displacement versus time graph could look like this, where you have an object moving away at constant velocity, and in which case it sweeps out a nice linear line on the displacement versus time graph. Now, in this case, positive slope implies positive displacement, and so our observer would be standing right here at the origin, watching this car move away. Now we can change things up, in which case we still have the observer standing right here, and in this case they're going to watch the car move towards them, and in which case the line that's going to be swept out is going to have a negative slope. So negative slope is going to imply negative displacement. The car is moving towards the observer. Now we can really change things up, and in this case the observer is still standing right here, and as the car moves towards them, we're still going to sweep out a line that has a positive slope, and in which case it's going to have positive displacement, and it's moving towards the observer. And to contrast it with a few other things that can happen, again, if we have the observer right here, the car can move away from the observer, and we can sweep out a line that looks like this. And the slope of this line will be negative, and that's going to imply negative displacement, displacement in the negative x direction. And in this case, again, moving away from the observer. So you need to develop these ideas of where is the object moving in relationship to some reference point. And in this case, it's usually the origin. Now, one last example is we could have a car that sweeps out a line that looks like this, and this point right here represents the point at which the object passes the observer. Notice the car continues to move in the same direction even as it passes the observer. And in this case, the displacement is always going to be positive, because it's always moving first towards the observer and then past the observer. Now, if we plot out where this car is as a function of time, if it starts here at the origin, then after 1 second, it will sweep out this displacement vector, moving a distance of 1 meter. But what we'd like to do is represent where that car is at a certain period of time. So we would put a little point here for after 1 second, it does move 1 meter, but it's at this position right here. After an additional second, it moves an additional 1 meter. And in this case, we'd put a point right here to indicate that at 2 seconds, it's 2 meters away from the observer. And if we continue to do this, first notice that the displacement vectors continue to point in the same direction, and they're all of equal length and in the same direction. So the displacement vector in each case is going to be the same. And again, notice that we're sweeping out a nice linear line. And in this case, positive displacement, and we're imagining the observer still standing right here. Now let's take a look at an object moving in the negative direction. And remember, Here we have the observer right here making the measurements, and in this case we're going to sweep out equal displacement vectors in equal amounts of time, and the velocity is going to be towards the observer. So again, negative displacement is going to tell us that the object moves with negative velocity. If we look at a displacement versus time graph for this type of motion, we're starting out 6 meters away from the observer. So the observer is standing right here, and this is where the car initially starts out. After 1 second, it moves negative 1 meters towards the observer. So it goes from 6 meters to 5 meters, and we'd represent where that object is at this particular moment in time, this 1 second, with this point right here. And again, we could continue to do this. Notice that the displacement vectors are equal in magnitude and in the same direction for each moment in time. It's moving with constant velocity, and so it's going to have negative displacement all along its route. And in this case, it's moving towards the observer. Now, the line that all these points sweep out would be a nice linear line. Now let's take a look at a velocity versus time graph for an object traveling with constant velocity. Now in the first case, let's say that the velocity was constant 1 meter per second. Now we have positive velocity, and in this case, if the displacement is positive, the object will have positive velocity. And this region down here is negative velocity, or represents negative velocity. So if the displacement is negative, the object will have negative velocity. So in the first case, when the object was moving away from the observer at a constant 1 meter per second, it would be a nice flat line. Now for this case, if we were looking at a velocity versus time graph, it'd be a negative 1 meter per second. So the negative is going to be indicating the direction in which the car is traveling. It's traveling towards the observer. Now, anything traveling with constant velocity is not accelerating. The acceleration is going to be zero, whether it has constant positive velocity or constant negative velocity. Both of those would be represented with an acceleration versus time graph, with the acceleration line going right across the time axis, which is indicative of the 0 meters per second squared. The velocity is not changing. Now let's take a look at the two different graphs that we made. So we made one graph in which the object was moving away from the observer, in which case the displacement versus time graph would be a nice linear line. And then we made another one with the initial position some distance away from the observer, in which case the object moved towards the observer, in which case the slope of this line was negative. The velocity versus time graph for each one also looked different. For an object traveling with constant positive velocity, it was a nice flat line above the time axis. For an object moving towards the observer with a negative displacement slope, the velocity was negative, indicating that it was moving towards the observer. And in both cases, the acceleration versus time graphs would both have lines right across the acceleration equals 0, or the time axis. Now let's just bring up one last example, in which case we're going to have two cars. They're going to both be moving in the negative direction, and in this case they're both going to have negative displacement vectors, and they're both going to have negative velocity vectors. So let's take a quick look at graphically how that's represented. So if we have these two cars, and again the observer could be standing right here, keeping track of where the cars are at each interval of time. If the cars begin to move as they previously did, then what we could do is we could sweep out equal displacement vectors for each of them, and notice the only difference between the two sets of lines in this case that are generated for displacement versus time graph for an object traveling with constant velocity is the shifting of where the lines are with respect to the observer. So the initial position of this car starts way up here at x equals 6 meters, whereas the initial position of that car would be right here at the origin. And then the final position for this car would also be down here. And then the final position for this car would be at the origin. And that just shifts the displacement graph up or down. So let's take a quick look at how those sets of graphs would be summarized. So in this first case, you have an object moving towards the observer, and then you have another one with the displacement of the object moving away from the observer. Now the velocity versus time graphs for both of those would be identical. They both travel with negative velocity. They have negative displacement or negative slopes in each case, and so they'd have negative velocity. And again, both the acceleration versus time graphs would be 0. The cars are not accelerating. They're moving off at constant velocity.